Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 31st, 2025, just yesterday. It keeps massive models from crashing by reducing signal growth from a factor of 3,000 down to about 1.6. The paper is titled mHC Manifold Constrained Hyperconnections. A manifold, which is a structured mathematical space with specific rules, ensures the training stays stable, and the implications for building huge foundational models are quite significant. Alright, Figure 1 illustrates how these connection paradigms differ in structure. The standard residual connection in Panel A is simple, while Panel B shows how hyperconnections add learnable mappings that can cause unstable signals. To fix this, Panel C introduces manifold constrained hyperconnections. These use green blocks to represent projection onto a stable mathematical space, which restores the identity mapping property, a rule that helps the model remember original input so information flows without exploding. Well, Figure 1 showed the structural differences between these models. Table 1 now provides an ablation study, a scientific method where researchers remove parts of a system to see how each part affects the outcome. The results show that the residual mapping HRES, which handles internal data flow, provides the most substantial performance boost. When all three mappings are combined in the bottom row, the absolute loss gap decreases further, reaching the best performance levels for this architecture. So, Table 1 summarized how different components affect performance. Figure 3 now illustrates the instability issues that arise when connections are not constrained. In Panel A, the single-layer mapping stays relatively close to 1, but Panel B shows the composite mapping, which is the total signal gain accumulated across all layers. You can see the blue line for the backward gradient exploding toward 3,000, clearly showing why unconstrained connections lead to massive training failures. Okay, while Figure 3 showed how signals explode mathematically, Figure 2 demonstrates the real-world consequences during training for a 27 billion parameter model. Panel A tracks the training loss gap, and it reveals a significant surge where the unconstrained version struggles. Panel B explains this instability by comparing gradient norms. These gradient norms measure the size of the updates made to the model during learning, and the blue line for hyperconnections shows massive, erratic spikes. In contrast, the manifold-constrained approach maintains a smooth, stable line, which prevents the training process from crashing. Transcript. Alright, while the previous figure showed the initial impact, Figure 5 provides a detailed look at training stability for the 27 billion parameter model. Panel A tracks the absolute training loss gap, demonstrating that the manifold-constrained approach reaches a final loss reduction of 0.021. Panel B looks at the gradient norm, which measures the magnitude of the mathematical steps the model takes to improve. The unconstrained hyperconnections exhibit erratic spikes in light blue, whereas the dark blue line for the manifold-constrained method remains as smooth as the baseline. This consistency is vital because it proves that manifold constraints prevent signal explosions in large systems. Annotations. Well, while Figure 5 showed how stable the training process is, Table 4 details the performance across 8 diverse benchmarks. The results confirm that the manifold-constrained hyperconnections consistently outperform both the baseline and standard hyperconnections. For example, in reasoning-intensive benchmarks like BBH and DROP, the manifold approach provides a significant boost. This suggests that the stability from manifold constraints, which keeps signals well-behaved, translates into superior reasoning in large-scale models. So, while Table 4 showed the performance gains, Figure 8 now visualizes exactly why the manifold-constrained approach works. The top row displays the unconstrained hyperconnections, where you see massive values for forward and backward signal gains. In contrast, the second row shows the manifold-constrained version, where almost all gains are near 1. This stability occurs because the mappings are projected onto a doubly stochastic manifold, a mathematical space where every row and column of a matrix sums to 1. This constraint ensures that signals flowing through the model remain balanced across every layer. Alright, wrapping up, manifold-constrained hyperconnections provide a robust solution for training massive foundational models without the usual instability. By grounding complex connectivity in mathematical manifolds, this method ensures that information flows smoothly even as networks grow. It marks an exciting shift toward more predictable and high-performing architecture design. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.